So once again, with polymers, well, both with metals and with polymers, but with polymers in particular, there's been such a tremendous evolution of materials and materials available. And so when you look at, from, the filament printers, the Ender 3D that you can get for $200 and what you can do with that. And then you see that, they're using, metals as a replacement plastic polymers for a replacement for aluminum and metal components. It's absolutely amazing the evolution that's taken place in the industry. And so our next speaker is Francesco from Roboze. Roboze is on the high end of the spectrum as far as the engineering grade and the high performance materials. That's become their specialty from birth, I believe. So we'll go ahead and turn the floor over to Francisco. Thank you very much, sir.
Thank you for the kind introduction. Hi, everybody. I'm Francesco Pantaleone. I'm the head of business development here at Roboze. Before we start, it's pronounced Roboze. I guess everybody was wondering. You wanted to do a LinkedIn post as well over it. So just for the sake of giving feedback to my marketing team, who has heard about Roboze in this room? Just don't be shy. Okay, a good 50%. So there is room for improvement. Let me see if oh, yeah. Thank you. Okay. Is there a way that they can visualize it? Yeah. Or maybe you can duplicate the. Yes, thank you. Perfect. Perfect. So thank you. So as Jeff was mentioning, we're going to talk about how high performance polymers and composites can reshape manufacturing. Roboze is an OEM fully focused on engineering and producing high performance polymers FFF printers at the industrial scale. So we are an Italian company, but we're based off Houston, as you can hear from my Texas accent. We're about 100 employees to date. We installed more than 350 printers worldwide, and we printed more than 25,000 parts through our distributed manufacturing network. So what is our vision? So as mentioned, we engineer since 2015 the highest performing polymers printing out there at the industrial scale. So you can see our flagship Argo 500 and Argo 1000, which is actually the largest high temperature, large format, high performance polymers printers out there, which is a mouthful. But we also have a vision to enable the true value of additive manufacturing, which is produce locally, close to the point of need, close to the point of use, on demand, right? Without that, the value of additive manufacturing in manufacturing is certainly diminished. So what we did, we leveraged our technology to build a network of manufacturers worldwide, from South Africa to Houston to Alaska. We're sending printers, and we're having a program for these manufacturers to print locally, but with global coverage with our technology and our materials. So to answer Jeff's question right off the bat, we focus where we know this type of polymers and the metal replacement opportunity can bring value. So what we have, what we call 5 pillars: aerospace and defense, industrial robotics, energy, motorsport and mobility, and medical. We highlighted in these 5 pillars applications and use cases where we know additive manufacturing of high performance polymers and composites can bring a massive amount of value. Why is that important? Because without creating value in producing with additive manufacturing, the management of change into switching from traditional manufacturing to additive manufacturing will be too steep to adopt. So we're pushing together with my team, the business development team, the adoption of applications in these 5 pillars where we know, and as you can imagine, the materials entice the fact that there is a focus on regulated industries and extreme environments. And that's where we want to focus on. That's where we specialize since 2015. Let's talk, before switching gears on materials, let's talk a little bit how we build the systems over the years. So we started in 2015 looking at what are the shortcomings of additive manufacturing FDM system, FFF. One of the things that we noticed was repeatability. So we patented what is the only rack and pinion system, helicoidal rack and pinion system, which is broadly used in traditional manufacturing in CNC, into high heated chamber for FDM printing of high performance polymers. What does entice? It entices the fact that we have outstanding repeatability, build to build and machine to machine, which is kind of unprecedented in FDM before. We introduce a PLC that gives us the possibility to remotely control the printer, to understand what the operator is printing, extract the G code if it's needed and troubleshoot it when it's needed, and as well to understand if there is any issue with the machine live. So instead of looking at what is the highest value or what is the highest percentage that will increase uptime for our users, we saw that downtime is a big part of it, right? Everybody talks about speed, but if I go 10 times faster, it won't make a dent if I impact the uptime of my production partners from 85 to 95%. And one of the things that we developed over the years is our insulated heated chamber, our controlled environment heated chamber, where not only we're not talking about an oven, right? Like my pizza oven at home. We're talking understanding the thermal flow on this environment to really induce the crystallinity level at the highest peak, on par with traditional manufacturing, on par with injection molding, especially for materials like PEEK. So let's deep dive a little bit onto 2 or 3 of these aspects. When we talk about the automate, we're talking about a 10-micron positioning accuracy. That doesn't equate to dimensional accuracy of the part, but it's a big variable. It is a big variable. And when we talk about 10-micron tolerances, we talk about repeatability of the systems, repeatability of the build. Will my part be like my last 20 builds? Like, will my machine in Houston print equally as a machine here in Connecticut, right? So there is that level of repeatability, which is on par with CNC. And there is 75% downtime that we calculated versus a belted system. Belts, by their own design, they tend to deform, expand, and contract, especially in heated environment. And if I need to have my operator going and measure and, you know, perhaps get a Gitter tuner app and see how the tension of the belt is for all the builds, I'm not sure I'm having a repeatable process. So we really kind of drill down into what makes parts repeatable. In terms of accuracy, to answer one of the questions that I see coming as it was in the previous talk, well, parts out of the build without any compensation and without any work will come into an ISO 2768 medium to fine class tolerances. Okay, of course there is room of improvement. We built a system where we have years, decades of data, especially on materials, temperamental material like PEEK, which tends to shrink and contract in a different way depending on the dimensions. The other things that we work on really hard was the controlled environment, right? As I mentioned, the heated chamber is just not an oven. You need to understand what is the thermal flow, how's that flow, how's that temperature homogeneous throughout all the build, right? Because if I'm printing parts for regulated industries, I need to know what the temperature DNA of each part is. Doesn't matter if it's printing on the top left corner of the build or the bottom. So what we did a study for an energy company where we print these 5 peak towers, and we measured at 3 different heights the mechanical performances of these peak towers compared to where they were printed. And there is very little deviation in the data. that gave that specific OEM the opportunity to qualify the process for extreme application, for an extreme application in the energy business. Now, one of the other things that we work, and it's on patent, it's our high viscous polymers extruder, HVP extruder. These materials are extremely viscous, right? It's like very thick paint. We had to understand one way to print these polymers for days, 4 hours, right? And you can see here we have about 4 kilos worth of a carbon peak bushing, and who processes peak knows how difficult it is to injection mold or print this type of dimension of peak. So how do we manage that? With the lowest amount of porosity. We built a system which is a little jewel within the machine, right? So it's 56 components in these extruders that helps with not deteriorating the polymer, with optimize the flow of the polymers, and actually it goes from 150 C to 450 C thanks to the compressed air cooling in the span of 2 millimeters. That means that we understand exactly what is the perfect Elson for these materials that will avoid clogging if you're printing for days. And that makes a difference on a large format machine and on a build production machine as our Argo 500. Now, talking about big, of course, we launched last year at Formnext, and it's going to be commercially available Q4 this year, our Argo 1000, which is the largest high temperature polymers, high temperature build chamber printer out there, right? So we took all of the technology and our core from the Argo 500 systems, and we bring it into a larger format, which was no easy challenge, because every time you go higher in temperature or larger in scale, your thermal flow will need to be readjusted. But we had good solid basis, and we scaled that into a 1,000 by 1,000 by 1,000 millimeters, so a cubic meter build envelope, which is unprecedented. So now let's switch gears on materials. Is there any question before we go on to materials on the technology? We can address it later as well. So where do we focus? We focus on the top of the polymer pyramid, having that says we have 12 materials, both from engineering thermoplastics perspective and standard polymers, common use polymers. But where we've been, let's say, engineering, what we're engineering these machines for is for the top of the polymer pyramid. So materials, especially on the semi-crystalline side, very temperamental, but extremely performing. So what we did right at the beginning, once we figure out the repeatability, we wanted to focus on materials that can close the gap with traditional manufacturing when it comes to performance. So they can be used as opposed to traditional manufacturing when additive manufacturing makes sense, right? When supply chain is a concern, when localization is needed, when customization is needed, where small part production cycles are needed, and that's what we want to focus on, right? So now when we talk about metal replacement, there is a lot of debate, right? Say, yeah, well, you can't really replace metal. I've been in metal replacement all my life. I've been working for GE Plastics, right, here at the Halley, and Sabic for over 14 years, right? So metal replacement is always a big topic, but there are certain conditions where high performance thermoplastics are such a better suited solution, right? So corrosive environments. And I'll show you some practical applications today so that you can really visualize where these materials are used. And the beauty of it is that this material and specific formulations can get to really perform as metal. We have materials that performs as aluminum alloys, but weighs a fraction. So again, lightweight opportunity. And as well, you know, materials that in corrosive environments, in chemical environments, are such a better fit than metals, stainless steel and whatnot. So which materials do we have? We have Ultem AM9085F for the aerospace, FSTR rate, FR25853 approved. PEAK, which is our flagship material. This is the most temperamental material, but as well the most performing material in the whole semi-crystalline sphere. Until we released the Helios PEAK 2005, which is a ceramic filled PEEK matrix, and then we'll talk about it in a second. We have carbon field PEEK, and we have carbon field polyamide. Those are the most performing materials we have in our portfolio. But we also have a set of functionalized materials, like for instance, the PC Lexan. This is a polycarbonate with siloxane, has 6 times more impact resistance than any other polycarbonate out there. So our angle of materials, now that we have a system and we build a system to process even the most temperamental materials at the highest grade. We print PEEK at around 35 to 40% crystallinity right off the machine. Now we can really go and look for functionalized formulation that can close the gap with traditional manufacturing in terms of performance, that can give a competitive edge to our customers and partners in terms of using different materials for specific applications, even on the engineering thermoplastic. After all, if we're all using the same machines and the same materials, well, you already know where this is going, right? So let's talk about Helios PEEK. Again, PEEK is the most performing material out there for chemical resistance, high temperature resistance, and mechanical resistance. Now, we build this formulation, and we do have compounding in-house. Material is a big part of our engineering. We have about 40 engineers working, and PhD and material scientists working on new formulation. Why? So material, it's application, and applications means expanding the use of additive manufacturing in a variety of fields, right? So is the quintessential element for us to scale the material. The material has about 40% more strength and stiffness than PEEK. There are specific fibers, very specific ceramic fibers that we develop with this material. Why? Because when you have a composite material, what you will notice is that there is always a kind of delamination from the fiber structure to the polymer structure. And that means that you increase the porosity. And that means that gives the external agents, whether it's temperature or chemicals, more space to kind of go inside that part and break the polymer chain. So we build that specific ceramic content, that ceramic shape, to make sure that the addition with the polymer matrix is the max as possible. So reducing part porosity and therefore increasing the strength of the material. So one of the beauties of this material is that the ceramic component actually comes off. So it's extremely easy to post-process, and it comes with a beautiful shine. It almost looks like a lot parts all out the build with just a light sanding. And we have, let's say here, a visual representation. You see that you're taking a PEEK part and you milk cut just with the flat head, you have a surface roughness of about 8 micron. With just hand polishing on the ceramic Helios PEEK, we have 4 microns surface roughness, which is quite amazing. And it takes really little effort. So where is this needed? Well, let me say that it has a great thermal and electrical insulation, even more than PEEK. So let's say that you need to isolate or shield from heat an engine compartment, and you need to do about a wall thickness of, let's say, 3 inches with PEEK, right? Now you can do the same, you can achieve the same results with 1.5 inch, right? Which is amazing for just reducing the dimension of your part, reducing the weight of your part, which ultimately for the type of applications in aerospace or motorsport where we're strongly present, it's quintessentials, right? You have the highest dimensional stability at highest temperature, so I have a very low seat coefficient of thermal expansion, and it's very easy to print and process. As mentioned, support comes off really easy, and the material can be surfaced really easy. Now, let's look at one application we developed for this material. So this is basically a pipeline inspection gauge, right? Pipeline inspection, when you have a new wells, you want to have, and the things that, you know, in that field, things are getting more and more, let's say, technologically advanced. So they need to have a structure that goes down on the well and actually measure how the well is cleaned, right? So in this case, we build it for lightweight and strong structure, extreme chemical resistance. This material has the best chemical resistance compatibility with all of type of agents, including Skydroll in aerospace. And of course, it has very low coefficient of thermal expansion at higher temperature. That means that if the more down I go in the well, the more heat there will be, the less the material and the part will expand. So ultimately, I have a dimensionally stable gauge for that application. Let's look at other type of applications that we develop, from structural component in aerospace to end-up layup tooling, and have a visual representation of that. So tooling for carbon fiber layup molding goes in autoclave under the ADC, 7 bars pressure, material is extremely stable. To interior, the classic interiors or hidden spaces use of 9085 in aerospace. For mobility, high voltage connector, good resistivity for peak. So we built a variety of electrical application for EV and for functional prototyping within the automotive sector, and as well motorsport. Positioning tools and calibration jigs in carbon PA. And what is the advantage? When our customers come to us and they make an assessment, and they want to have an assessment, the way we work is we go for a technical feasibility. So what are the CTQs of the applications, and does it make sense to print it in these materials? In this case, we offset injection molded polyamide, and we went basically from the capability of do 7 cycles to 20,000 cycles with a big solution for the E-axle E-engine from Bosch. Another cool application in automotive is basically this fixture in PEEK. This company, Iveco, was used to have like these kind of blocking fixtures for the door. This is a painting booth where they use stainless steel. Now, what happened is that stainless steel, the paint on the stainless steel will actually attach to the metal and will kind of layer up, right? So the gauge will need to be clean. But the problem is that it will also corrode with the harsh chemical environment. So we printed the same jig in PEEK. There was no need to PEEK as very good self-lubricating properties. So nothing pretty much sticks to PEEK. And they could wash it in autoclave, whatever they needed, without losing performance. So they went to changing 10 jigs a week into using one that lasted 4 months. Development in the space industry is, of course, when we talk about lightweighting and when we talk about performance, is one of the most interesting industry that we can serve with these polymers and the metal replacement. So we work for the super pressure balloon 2 project of NASA, and as well for the CubeSat for University of Colorado Boulder, really helping them reduce the payload on these materials and combining geometries, combining the value of really of additive manufacturing, of putting multiple parts together and replacing metals in this type of application. The material has very low outgassing. It passed all of the conditions that are needed to be launched in orbit, and actually the CubeSat, I think, is going to be launched in the next couple of months. Chemical environment, this is where these materials shine, right? So this, what you can see here, this is basically a prilling shower for chemicals. And here, I mean, talking about the challenge of metal replacement, right? So imagine the context. This is a 40-year-old plant with all the equipment. Now, the only plastic part you can see is the part that we printed. Everything was metal. Everybody was thinking metal, right? Now, the resistance on this project was outstanding. Like everybody said, this is not gonna work. It's plastic. I had literally guys taking the plastic parts and smash it on the ground to show the plant manager, man, this is not gonna work. So we work with the EHS manager, with the site manager, with the plant manager, really to let them understand why they should be implemented. They were working in a conditions where maintenance was required. So these were 23 kilo stainless steel showers that needed to be disinstalled every 2 days and need to be chiseled out, basically the chemical that is produced into this shower, because it will crystallize on stainless steel, right? So with PEEK, we removed that. So we decreased the maintenance time tremendously. But the good thing is that not only the EHS manager was happy because they had to have 2 operators lifting these parts, and now it's 6 kilo, 12 pounds, right? So you can lift it with one hand. But the other thing is that material improved quality because of the flow of the material with this type of component. So again, created a massive amount of value for the customer with metal replacement application. And they went from 500 tons a day to 700 tons a day production. So not only reduction of maintenance cost, but as well, improving the top line, increasing their revenue with that solution. Another type of application in manufacturing, this is for automotive, is end-of-arm tool. I think all of you have seen. What is the value of metal replacement here? Well, I can work in more compact environments, especially when we're talking about a series of robotic arms that needs to work in constrained space, and we can reduce the weight by 56%. That means that imagine you have a robotic arm that has 100 kilo payload, and you have a jig that weighs 20 kilo, but your final part that needs to be moved is a few hundred grams, right? Here it means that for this customer, we went from 100 kilo payload to a 20 kilo payload. So we're talking about 100 plus K worth of saving for them in implementing the metal replacement solution. This layup composites tool, again, we did a study on which material will be the most resistant in autoclave, and this is the part that is out there, so I invite you to come. The material was tested for autoclave curing, so under the ADC, 7 bars pressure, and didn't deform and didn't contract or expand. So the parts that were, which is basically a kind of a clamp for the canopy, for the aerospace structure to be bolted to the canopy, it was dimensionally accurate after several cycles of autoclave. Other ideas on how, for instance, it's probably me, it's you, okay. Presso forming of aluminum sheets. I mean, this is a no-brainer. The material has a very strong compressive strength, so it can be used as well for metal forming applications. And then spare parts. I mean, as simple as a backup sealing ring can be, right? Okay, why would you use additive for that? Well, in traditional manufacturing, these when they need a backup sealing ring, which is basically a seal that helps all these rubber sealings into the valve not to extrude, right? So it's just maintaining that seal in place. Well, they need to have a full billet compression mold, and the material is expensive. So typically it takes 20 days to up to 2 months, depending on the size, and they machine 70% out of it. Now we can do a near net shape. You still need to machine it for tight fit. I mean, those are applications with zero clearance type of dimensional accuracy, right? So they need to fit there, and there is a certain requirement on surface roughness. But you can do a near net shape in about 5 days, completed, machined, and delivered to them, which is of a huge amount of value. Because imagine that if they don't have that specific backup sealing ring, and there is kind of a failure, and that part of whatever that pump is kind of extracting, it fails, this is millions of dollars per hour that segment is stopped. So again, even with non-complex part, you can extract value, you can generate value in these specific industries with metal replacement. So Roboze 3D Parts is our platform, manufacturing as a service platform, where companies can order in a very flexible way, locally and on demand, these type of components. We have our application engineering team that is helping with the technical feasibility. Business development team will help you or your customers understand what is the value that there is in using this type of application. And we have global coverage and local delivery with, to date, more than 20 partners worldwide. And with that, I will open for Q&A. Right. That's a great question. And again, as a material guy, I get asked all the time, say, how's this? Was that? Yeah. So the question is, how did the supply chain issues affected material availability for these type of polymers? And the answer is almost none. The reason is there is a process of transformation of these polymers. First of all, the quantities that we use in additive manufacturing will never account to the quantities that are used for let's say mass manufacturing, like in automotive. So that's where more of the pressure is, the automotive space. For us, and for our material supplier, this is high value type of business with low volume commitment. So there is no really an impact there from our side. Okay. Any other question? Your business model. If I wanted to invest in one of your companies, then I also can become a service bureau based on that. Absolutely. So, and typically we partner with, so the question is, if I purchase one of your machines, can I become a Roboze 3D parts partner and manufacturer and be part of the, let's say, on the localized manufacturing network? Yes, we work with manufacturing companies that utilize these materials or have a specific specialty in their core business. Let's say they're an ITAR facility, they serve our space, they know that with these specific projects, we know that they will be a good fit. So there is a kind of selection process to get into the Roboze 3D parts network. But overall, we give local companies as well here in Connecticut the possibility to become one of our 3D parts partners. Very well. Thank you. Thank you, everybody.